Thanks.
Okay. So hi everyone, my name is Pranav Karthikeyan. I'm a junior at Poolsville High School, and I'm also the junior captain on Team 4099, which is based out of Poolsville, Maryland. So this presentation is going to really talk about like an introduction into vision with Apriltags and going from knowing nothing about Apriltags to implementing it into driving to positions on a grid and scoring cones. Okay. So the overall agenda of this presentation is to talk about what is vision looking like in FRC and what is an Apriltag and what is retroreflective tape and why we should use Apriltags over retroreflective tape. Also, we're going to talk about how to detect Apriltags, different ways you can detect them, different hardware, software, cameras. How do you use Apriltags within your robot code and how do you implement Apriltags, as well as any debugging and some demos we have lined up. Okay. So right now within FRC, Apriltags will be your only source of vision targets on the field. There's going to be no more use of retroreflective tape for any detection on targets. And this is actually pretty good because retroreflective tape in theory is like really flawed. There's a lot of tuning that's necessary between fields and because the lighting changes between fields. Also, there's a lot of false positive detections based on like detections tape, other shiny objects within your camera field, as well as the green light that shines off a lot of our vision tape, and a lot of our retroreflective devices can hurt drivers' eyes if that tape is really close to the driver area. So we should initially go over the overall idea of an Apriltag. What is an Apriltag? So an Apriltag is a visual fiducial system. So what that means is it's a tag that's referenceable, distinguishable, and recognizable from a camera's perspective. So you've seen Apriltags before, or forms of Apriltags, which are just fiducials, in the idea of a QR code. So a QR code is something that a camera can easily reference, distinguish from other QR codes, and is able to recognize and scan. And so you're able to get data out of different fiducial types. And with QR codes specifically, you can use them for 3D pose estimation. So what is an Apriltag solving and why is it replacing retroreflective tape? So an Apriltag gives you an easier to detect and more open source detection software or solution because there's a lot of tools out there for detecting Apriltags, and it's not an FRC specific tool. This is used within all sorts of robotics and industry. There's a lot less tuning necessary in order to like use Apriltags because a lot of the actual algorithms behind it are less, they don't get changed as much based on the environment you're in, like the lighting or the amount of contrast in your photos. Okay. So it's important to understand what does an Apriltag actually give you, because we talked about a pose and we talked about the 3D pose estimation idea. We should kind of go over what is a pose and what is a tag ID and all the other stuff you need to know before we get into pose estimation. So for an Apriltag, every tag on the field has a specific ID. That ID is different for each tag. It's different for each one of these tags right here. And that each one of those tags will represent different locations on the field. And each one of those tags has 6 degrees of freedom, which is the X, Y, and Z length, as well as the roll, pitch, and yaw. So a tag has a specific pose. A pose is just 6 degrees of freedom, X, Y, and Z, roll, pitch, and yaw. And you can get this data from the tag and understand where is that tag, where are you, based on looking at that tag. And that can be used for detecting where your robot is, which we'll go into more on the later slides. So another thing we can talk about here is ambiguity. So ambiguity can be described as if you're able to look at a tag and the location of a tag, how certain are you that what you're looking at is at a certain location? So in this example here, we have a drawing of a rectangle, drawing of a general sized Apriltag, and then we have 2 boxes around it, one in green and one in blue. These boxes represent 2 different ways of looking at that tag that can represent 2 different locations, even though you're looking at it from one perspective. So that's pretty ambiguous. You don't really know where you're looking at that tag from, right? So that means that tag detection is going to have higher ambiguity compared to one where it's just one of these boxes. So this may not make sense right now in how you actually use this information, but it becomes really important in the future. Okay. So another thing you need to know is there's different families of Apriltags. If you just search up an Apriltag, you'll get a lot of different things like 36H11 or 16H5, or even circled Apriltags or Ruco tags. And it's really important to understand what are the different families and the different uses between them. So currently within FRC, there's generally been 2 main families, 16H5 and 36H11. So in the past year in FRC, you've seen a lot of these 16H5 tags, which are bigger blocks of data. They store less data, so you can have farther detection distances, but there's higher false positives, and overall, you can have less of these tags on the field. Whereas 36H11, which is used within, I believe, FTC, as well as generally within robotics, it can store more data within the tag, so you can have a lot more unique tags. Because there's 36 bits of data within a 36H11 tag versus just 16 bits on 16H5. So with this increased amount of data, that also means you have a lower detection distance. So you're going to need more tags on the field if you want to have better pose estimation. So just to go over the notation of how a tag family works, the notation is bits, H, and then Hamming distance. So Hamming distance represents how many bits can be flipped until you get a different tag ID, which in this case for 36H11 is 11 bits, and for 16H5 is 5 bits. That information is not necessary. All you have to know is 36 has more bits, which means it's a lot more specific. Okay, so something else to go over is the difference between camera extrinsics and intrinsics. So camera extrinsics is the location of the camera that's detecting the tags relative to the 0 or the origin of your coordinate plane or your reference plane, right? So if we're talking about a robot, your origin position would be like your robot origin or like the center of your belly pan. And then your camera position would be some X, Y, and Z off of that center location. And then your intrinsics is referring to like your actual camera itself. So your camera has a bunch of different stuff, like its focal length or its optical center of the actual camera lens. And you have to always account for that when you're actually doing the math for figuring it out, like and doing pose estimation work. Additionally, cameras will also have distortion within the lenses. The actual glass within those lenses will slightly warp the light coming in that's going into the sensor, and that can make lines a bit curved or not curved. And you see this a lot with fisheye cameras, right? It's not software that's actually making these like these photos pretty fisheyed. It's actually the lens itself and the fact that it's curved, curving the light in and making it like easier to have a larger FOV. But that also means lines will end up not being straight. And that's a really big issue when you're working with pose estimation or when you're working with Apriltag detection. So you also have to account for that distortion. So when we're talking about camera calibration within FRC, generally it's referring to getting the intrinsics of the camera as well as the distortion of the camera and combining that into one camera calibration file. Okay, so over time, there's been a lot of different software generated for doing Apriltag detection. You have the Limelight OS, Photon Vision, Northstar, and other custom software. So it's really important to know what fits your team really well, what's going to work better for your needs, and what you should select for the upcoming season. So this is going to be done in order of easiest to hardest to do. And so the first one is Limelight OS. In my opinion, Limelight is probably the easiest Apriltag detection software to use, just because a lot of the work is done completely for you and is really just easy to use out of the box. So Limelight OS is a fully built Apriltag-like detection system. The camera is fully built into the system. All the hardware to detect is fully built into the system. It's just an Ethernet port, and then you just power it, and then you can get data out of it immediately. So that's one of the benefits, is that it's completely built for you with a really nice code library to use. It also has other stuff. If you want to use machine learning, it has options for machine learning. You can upload machine learning models. It can detect stuff. The camera has a really nice FOV that works pretty perfectly on fields. And FOV is just the zone that a camera can see. So a wide FOV would be like a fisheye lens, and a really close FOV, you can only see stuff that's directly in front of you. So another thing on the Limelight 3 that's really, really good, that's changed between Limelight 2 and Limelight 3, is the FPS. So when you're detecting Apriltags, it's really important that you have high FPS or high frames per second. So that's the amount of detections that you can get per second. Sometimes if you have like 5 or 10 FPS, your readings that are coming back from your camera will be way too late. And you'll be getting data that's like pretty far in the past and doesn't really help you with like getting really up-to-date pose information. So the fact that you can get like 50, 60 FPS on a Limelight is really important, because that just means your pose estimates will be a lot more accurate. So one of the big cons with using Limelight 3 is that it's $400, which means it's kind of expensive and inaccessible for a lot of teams. Some of the higher level teams, you'll see them use 3 or 4 different cameras, or 3 to 4 different limelights on their robot. And that's that works for them because they can pay for it, but for a lot of teams, that's not really accessible. So another option that's a lot cheaper is Photon Vision, which is completely free. Photon Vision is an open source software for Apriltag detection. It's built as a jar file that you just upload to your software, and then you just set it up using 4 Linux commands. And I can't stress enough how easy it is to set up. Like, the guide on the Photon Vision website will help you set this up in about 5 minutes. It's also really powerful. It uses the Aruco algorithm, which is an OpenCV Apriltag detection algorithm, and it can support multiple cameras, which the Limelight can't. One of the cons is that Photon Vision is just a software. It's not a completely built package, meaning that you also have to provide your own hardware, you have to provide your own camera, and you also have to provide your own networking stuff. So, and the other one is that camera calibration on Photon Vision, it's provided out of the box, but it's kind of weak. And if you probably want to use a different tool in order to actually calibrate your cameras. Okay. North Star is another tool that you can use. It's used by a lot of higher level teams for their Apriltag detection work because it's a lot more customizable compared to Limelight OS and Photon Vision. So North Star is an Aruco-based Apriltag detection tool made by 6028. And one of its benefits is that it's really lightweight. It's just, I think it's like 8 Python files that you just run and you set up as a service on Linux. And it's highly customizable, but it's configurable over network tables. So if you want to edit your camera exposure or your gain on your cameras, that you can just do that over network tables. But if you actually want to edit the code itself on your Apriltag detection system, you can do that just by SSHing in and then changing a file and then restarting your service. One of the cons about this, like Photon Vision, is that you have to come up with your own hardware and your own cameras. But the main issue is that's not really docs for this. You just kind of have to ask Jonah whenever you need help. And so this is kind of a problem because it's really hard to do this if you don't have a lot of knowledge in Linux, a lot of knowledge within the actual Apriltag detection work. And one other thing that it doesn't have that the other 2 options do is that it's GUI-less, meaning that you can't really look at what's happening. You can't really edit different stuff on a website. You kind of just have to go into code or just go into the camera preview. Okay. The last option is Hawkeye, which is 4099's old solution last year. So we ran this before the 2023 season, before we switched to North Star. And the whole goal of this was kind of just to test how easy it is and what are the other hardware devices we can use in order to detect Apriltags. So Hawkeye is an Apriltag detection system that uses Android phones. So we can do pretty high accuracy readings because we can use the high resolution cameras on Android phones. So at 6+ meters, we were getting relatively high accuracy and getting around 30 FPS on a Pixel 7. And then we were getting the same on a Samsung S21. So the whole goal of this is not really to show the feasibility of kind of using an Android phone within an actual FRC match. Is more to show that the Apriltag detection algorithm is a lot easier to implement on different devices compared to retroreflective tape. And that's a lot more open boxed and it's a lot more industry focused. So there's a lot more tools out there that you can just apply within your FRC robot to make Apriltag detection software work. Okay, so now that we've kind of talked about the software that you can run, it's really important to talk about the hardware that you can select. So the first one is the Orange Pi. So the Orange Pi is what we use on 4099. It is a RK3588 based single board computer. So I believe the Orange Pi 5B is the best performance in its current form factor, which is just a Raspberry size board. And it has a lot of I/O as well as a really great chip on there that can do a lot of really good CPU work as well as TPU work. And it's really small, so you can fit it basically anywhere in your robot. Last year, 6028 put it on their double jointed arm. We put 4 of them on our belly pan this year. And there's a lot of really good accessories that you can use. So there's heat sinks built for the Orange Pi that can cool it down because it almost reaches its thermal throttling temperature between matches, as well as fans that you can put on there to cool it. One of the main cons is that unlike a Raspberry Pi, Orange Pis have very little documentation on the actual hardware itself. So unless you can read a lot of the PDF documentation that they have, it's kind of hard to understand why something might not be working, why your Wi-Fi might not be working, why you can't use machine learning models or certain chips on your Orange Pi. So that's not really something you have to worry about if you're using something like photon vision within your Orange Pi, just because you just set up 4 commands and then it almost always works. Okay, we didn't put the photo in, but B-Link is another option that you can use. So a B-Link is a slightly larger version of an Orange Pi, but it's more boxed off. I'm not really too familiar with the exact benefits because we haven't used it before, but the benefits, I believe, are it has a GPU that you can use for processing work. It has a slightly better processor than the Orange Pi, so you can do more cameras, but we saw that it gets worse frame rates and it's also larger, but you have to power it the same way. Yeah. All right. And the last hardware tool that you can use is the Limelight 3. So the Limelight 3 is a really compact COTS product and works right in that box. And I want to stress that the Limelight 3 is different than the Limelight OS. Limelight OS, the software that can only run on Limelights, whereas the Limelight 3 can have photon vision running on it. And because of that, you can use the hardware within the Limelight as well as the software on photon vision. So you can kind of do these mix and matches between hardware and software, which is something that you should know. So one of the benefits of Limelight 3 is that it's extremely compact. It's much smaller than an Orange Pi because it has all the camera built in, it has all the like compute boards built in, has a fan built in, and all the I/O stuff as well in a really, really small package. It also works with the Google Coral for hardware acceleration if you want to do machine learning work or if you want to do any GPU Apriltag detection work. One of the cons, like we said before, is that the Limelight is extremely expensive. It's $400 for one of these. If you want to use a Coral, it's another $100. So there's a lot less room of like error. If you can't really like break one of these, it's kind of like important that you keep it safe. And there's a lot less room for learning just because the Limelight 3 has a lot of stuff built out of the box. So you won't be learning much about how to pick different hardware, how to pick different software. Okay. Do we have any questions so far? I think there's 2 in the chat. Oh, never mind. Okay, I'll just continue. So for camera selection, we're not really going to go over the different cameras that you can pick. We have 2 good ones up here, but there's a couple things that you have to make sure you're looking at when deciding what specs you want to pick for your cameras. So the first one is image size/resolution. So the larger your image size is, the more resolution that you have in your photo. That means you're generally going to be able to detect tags from farther distances just because the tags will be a larger amount of pixels within the actual frame of your image. So in this case, this year, we picked the 50 FPS 1600 by 1200 OV2311 camera from ArduCam. And this camera, just because it had that larger frame, we were able to detect tags from, I believe, a larger distance. I don't know the exact amount, but we were able to get longer distances. And that's also something that worked really well this year just because there were less tags on the field. The next is shutter type. So shutter type is actually, in my opinion, the most important spec on here, just because global shutter reduces the overall amount of motion blur that you're going to have within your tag detections, which you're also going to have within your images that you're taking from your camera. And the really important thing to talk about this is because if you have a really fast moving robot across the field, and then you also try to take photos with a regular camera that doesn't have global shutter, you're going to have a lot of like tags which are stretched apart, a lot of motion blur within your tag detections. And so that's actually going to make it really hard for you to see any tags, or if you do detect tags, like the corners are going to be really far off and then the accuracy is going to be terrible. So it's really important that you pick a global shutter camera, or if you don't, you should try to only use like your Apriltag detections when you're moving at a really slow speed. Okay, so FPS. Yeah, so one of the really important things about FPS is just that it's kind of comes in the opposite of resolution. So when you're getting a camera that has like 4K or 1600 by 1200, generally they drop the amount of FPS that you can get just because global shutter doesn't really work well with high resolutions and really fast FPS. So generally, you kind of have to balance like the amount of FPS you want with the amount of image resolution. So if you have a lot of tags around the field, you don't need as much image resolution, but you might want to get more vision updates. So you might go for a higher FPS. So that's kind of generally how you want to balance it out. There's also a couple other things like size. So the life cam has a different size compared to an Ardu cam. An Ardu cam can fit, you can fit multiple within the palm of your hand. A life cam is a bit bigger than that. It's a bit bulkier too. You might not be able to fit it in certain places. Output type is also really important. You see a lot of teams using the ribbon cables that go into Raspberry Pis. I'm not really a fan of that just because ribbon cables can be pretty delicate and the actual connectors themselves can be pretty delicate. So we try to stick with the USB just because it's also easier to put into a computer and actually calibrate the camera and then put it back into a Orange Pi. The last is color. When you're doing Apriltag detection, the actual like algorithm behind it never works on color. It only works in monochrome. So it's really important that either you select a camera that is doing monochrome immediately on the sensor itself, and then the image it's sending off the camera is monochrome, or you're doing the processing off board on your software. We picked doing all the stuff monochrome on the camera just because we felt whatever image is coming out that will be better than an image that's converted. Like there might be like less image quality loss. And I don't really know if that's a true thing. I know 6328 also like said something similar to that. So yeah, if you want any more research on that, you can go for it. Okay, so here's kind of like the main area that we want to talk about. Oh, I guess I missed this area. It's kind of recommended, and most teams do pick the OV9281 camera just because it's a lot cheaper. This is about half the price. But if you do want to go for larger image detections, the OV2311 works the same. It's the same form factor. It'll look the exact same too, but it'll be double the price, around $100. Okay, so pipeline. It's really important that we talk about how do we use all this hardware and software and cameras, and how do we take the data that we're getting from our software and putting it into a format that we can use in order to actually score points. So the first thing we need to talk about is hardware and software configuration. So within an Apriltag detection environment, or like wherever you're doing your Apriltag work, you always have to configure the following like environmental specific variables. The first one's exposure. So exposure is kind of talking about just like the amount of light that's going to the camera. Resolution is you want to make sure the resolution of your Apriltag detection system matches up with your camera. So if I'm telling Photon Vision to detect at 640 by whatever 320 resolution, but my camera itself can do 1600 by 1200, you're not fully utilizing your actual camera's hardware. And you're actually doing a bit more work because you have to downscale those photos in order to fit, right? So you always want to make sure that you're picking the right resolution. Sometimes you might want to downscale because your hardware can't keep up with the size of your photos, in which case you're going to downscale, but sometimes you don't need to, and you're kind of just losing a lot of resolution with your photos just because you're downscaling. So the last one's contrast. So you want to have a good amount of contrast between your photos. You don't actually need to edit this as much just because Apriltags are black and white. They're a lot easier to detect and a lot easier to tell apart from the environment. And the last one's brightness. If your scene is really dark, you should increase the brightness of your photos. I know these are all settings within Photon Vision. Generally, between competitions, we've tweaked these very little. I think we've tweaked exposure a bit and maybe gain, but other than that, it's been like not that much. You also have to make sure your camera is focused so you can see the exact edges of your tag and they're not blurry. Because the way the Apriltag detection software works is that it looks at the corners of your tag in order to detect the pose of your tag, right? So if your camera is blurry or it's like not calibrated properly, these camera corners or these tag corners are going to be slightly off, and that's going to make your detections off. So like I said before, camera calibration also has to be done. This can be done through a bunch of different softwares. This kind of out of the scope of this presentation, but if you want me to talk about it at the end, I can. But there's a bunch of different ways you can calibrate your cameras, and some get you better results than others. Okay, so getting data to the robot side and actually processing that information is it's pretty easy to do based on the different software that you're using. So generally, all this data is getting sent over network tables, and it's either being published as like a straight JSON or as a list of doubles, which represents the pose of that your camera is getting, right? So based on the software that you're using, it's going to come in different formats, which is why you should always read the docs instead of assuming what's happening. So PhotonLib does a lot of the work for you. If you just tell it what camera, if you just like, you kind of instantiate a camera object, and then you just put that into the photon pose estimator, which returns like your actual robot pose based on like a transformation of your camera. So let me go over that at the end, but LaminateLib does the same thing. You can get your camera pose, and then you add your camera transformation in order to get your robot pose. And then Northstar, you get a double list, which you have to convert into a pose object and add your camera transformation. So if anyone's not clear on what a camera transformation is, that's the camera extrinsics, right? So that's the distance from your robot origin, which is represented by this point right here, UV, to the center of your X, Y, and Z of your camera, right? That's like generally the lens of your camera, which is kind of like the center of your photo. So if you're able to figure out that distance, right, and we're able to get the camera to a tag, if we're able to add the transform between the robot and the camera, then we can get the distance between the robot and the tag. So it's a bit of vector math right there, but by doing that, you can just get the robot position, which you're going to be doing all your math on. Does that make sense so far?
Can you talk a little more about calibration? So if I have two of the same camera, do I need to calibrate them both independently, or are they going to be close enough?
Yeah, so generally it's good that you calibrate each camera differently. The calibration process is really easy to do, so it's recommended that you do it differently on each camera. So on Photon Vision, what you have to do is you just go to the camera calibration page, and then all you do is just take like 16 different photos of something called a Chirurco board, and that'll calibrate your camera. And the reason this is different is just because the distortion within the lenses of each camera will be different, because the glasses will be made slightly differently each time. There'll be imperfections within the lens. All that sort of stuff will make sure there's different calibration constants. And then if we want to go into more about how we do camera calibration, there's a bunch of different software that you can use. So OpenCV provides their own camera calibration tools. You can just take a bunch of photos of a Chirurco board, which is right here, and then it'll just figure out your camera, like your distortion matrix, as well as your camera intrinsics matrix. And then if you use something like MATLAB, you can just upload the photos, and it'll visualize your camera extrinsics as well as your camera intrinsics. And you can kind of use this to like throw away certain photos that are making your calibration worse. And so the whole goal of camera calibration is to reduce your reprojection error, which is kind of a measure of figuring out if light is coming to the camera, is my camera model accurately reprojecting that light back out to where it's supposed to be. So it kind of tells you if your camera model is able to represent your camera within like math properly. So if light's coming in and then I use my camera model to like estimate where that light came from, how accurate is that math, right? How accurate is that reprojection compared to where it actually came from? And so you want to lower that reprojection error as much as you can, because that reprojection is used for the actual detection of Apriltags and getting your pose like information. Okay. All right. When you detect like a robot pose, it's really important that you work on rejecting these poses properly. Just because if you get a bad pose estimate from your camera, like someone's blocking a corner, or you had a really ambiguous pose, if you put that into your pose estimator, which is actually trying to get your final robot pose, that can kind of mess up like your actual robot position. It can do a lot of bad things. So we have to figure out how we properly reject a pose. So when we're talking about pose rejection, we're talking about measuring the error between measuring certain values of that estimated robot pose compared to where the robot actually is, or where we think the robot actually is. And if it has certain things that are different, we're going to reject it. We're not going to put it into our pose estimator. So stuff that we do is like if the total distance of the estimated robot pose from the actual Kalman filter robot pose is more than 2 meters away, we just reject it. We don't use it. Or if the rotation of our camera pose or or robot pose is more than 7 degrees off, we also reject it. And we reject readings that are off the field completely. So if it has like a negative X or Y, it's off, or it has too big of an X and Y, it's also off. As well as if the Z axis is not close to 0, then we also reject it, meaning if it's way too high, if it's above the field, if it's way below the field, it doesn't need to be added. Okay, so now that we know what tags we want to detect, right? We know, now that we know our robot pose and we know different robot poses from different cameras, how do we put that into one final robot pose that we can actually use for any sort of point scoring work? So that's when Kalman filters and point clouds come into play. So when we're kind of estimating poses, we have a bunch of different sources of data that we have to put together, stuff like our odometry, our different camera detections, retroreflective tape, as well as game piece detections. So a Kalman filter is able to take different sensors or different types of sensor inputs in order to get one system state, which in this case is your final robot pose. So to go into what the WPI pose estimator wants, it takes in your current robot pose, which is where the robot is at that time. It takes in the latency, meaning when did the tag actually get detected in the camera? Like when did the light go into the camera lens to, that instant in time where it's actually going into the pose estimator object in WPI-lib. That value actually matters because if you consider that pose that the camera just detected as being accurate up to that instant, it's going to account for a bit of error, or it's going to not account for the fact that the robot has moved in like the roughly 11 milliseconds since the actual camera detection. If that doesn't make sense, let me know and I can clarify that a bit more. But the next thing you also have to put in is standard deviations. So standard deviations generally measures the amount of noise in like your measurement type. So if I have something like odometry, that's going to have a lot less noise within the detections compared to something like Apriltags or game piece detections. So my standard deviations for something with less noise like odometry will be a lot lower. So I'll have values closer to like 0.05 or 0.025, whereas cameras will have higher standard deviations just because there's a lot more error, meaning that I'm going to have something close to 0.35, 0.5, 0.75. So there's two different pose estimators they can use. Both these implement Kalman filters, but the way that they take in the data and the process of the data is different. So we have the WPI-lib pose estimator, which is built into WPI-lib, and it's part of the Swerve Drive pose estimator. So you just do add vision estimate, and then you pass in your estimated robot poses, as well as your standard deviations and latency, and then it'll put that in, and then it'll compute that into your estimated robot position. So the kind of issue with this, or the one flaw, I don't know if this is fixed yet, but every single time you add a vision estimate, it'll recalculate your robot pose, which is kind of an issue if you have multiple cameras, if you're doing like retroreflective tape work, or if you're doing like game piece detections, because if you add something like 6 vision updates for, however many different sources of odometry that are sources of like pose input you have, it'll recalculate it every time. So you might be doing 6 different iterations of your Kalman filter within one loop cycle, which is going to take up like a considerable amount of milliseconds. Whereas 6028's pose estimator, it'll get you the same output, but it'll only do it once per loop cycle, which is a lot more efficient. Okay. Let's get to that. All right. So it's kind of important to talk about how to use PID in order to align with the grid, right? Because now that we have this really strong vision system with all this hardware and software, as well as a really good accurate robot pose, we should use this data in order to go somewhere and drive there properly, right? So we can use our proper current pose in order to autonomously drive during teleop, and we can do this just using PID. So because we know our current robot pose is what we feel is the most accurate based on the Apriltags, we can just do PID on our X position, as well as our Y position, and also on our theta compared to our target. And so the distance or the difference between our target X and our target Y will be our target X and our robot position X, or target Y, robot position Y, target theta, robot position theta. Those will all have PID accounted for on each one the error amounts in order to go to a certain position on the grid, right? So you can just use, I think the swerve drive, like there's like a class within WPILO where you can just pass in like a controller for X, Y, and Z, and then it'll give certain like states for your swerve modules that you can drive to. And you can tune your PID constants in order to drive these positions. You can also do closed loop control on your Apriltag work if you generate a trajectory for it to follow from point A to point B, and then you can follow that using some feed forward values for your wheels as well as PID. So you don't necessarily need to do that. If you're just on a straight line, PID will work perfectly fine for you. But if you want to do farther away movement, if you want to do curves, stuff like that, it's really important that you use something like a feed forward as well as PID. Another thing to note is if your robot pose isn't correct, then if you're going to be applying PID to something which already has error within it, so you're not going to be able to get exactly to your target position. So it's really important that you work on getting an accurate robot pose first, and then using PID in order to do stuff like score. Okay, so what does this look like in practice? So a couple of weeks ago, we got a really good fast system for scoring working with Apriltags. And all you have to do is just press a button, and then it drives over it using feed forward and PID, and then it can go and score. So this system has 3 different cameras on it, as well as 2 tags on the field. And we're also using the odometry offer modules in order to put this all into one pose reading, which we're then using in order to drive over to a certain position and score. So what does this look like within like an actual like robot code thing, right? So we talked about like how we can have different robot positions, and we have to estimate this using a Kalman filter. So we can actually visualize this directly. So we can see here at this moment, we have a bunch of different robot poses reflected by the green drivetrains. And so each one of these is a different camera reading of where the robot is. So like one of these is North Star 1, which is camera 1, North Star 2, camera 2, North Star 3, camera 3, right? And then as we play forward, we can see these robots are farther away from our estimated robot position when we're farther away from the tags that we're detecting. And as we get closer, they all basically pretty much line up. And the main reason for that is when you're farther away from the grid, you're going to have like overall more noise within your photos, which means worse Apriltag detections, right? So when we're closer, all like multiple of our robots will be stacked on top of each other perfectly, meaning that we have really good accuracy, which is really good calibration, really good camera transforms, and really good standard deviations, pose rejection, all that sort of stuff. And if we want to look at what tags we're actually looking at, we can do that here. So we can represent these as vision targets. And then this one right here is an actual tag. It's in a different position in the field. So when we're driving around, we can see we're seeing both of those tags. And then we have a lot more error around the charging station, which is fine just because the angle we're at, we only have one camera detecting right now. All that sort of stuff will lead to having error. But when we get closer and we actually start driving over, we have our tags starting to line up. And this is not really in the scope of the discussion, but you can use AdventureScope really easily for tuning your Apriltag detection system. You can look at the error between your X and your Y and your Z of your camera relative to what you actually know. You can easily read this data within AdventureScope. It'll just show you the values here, and then you can just figure out if that's right or wrong, as well as look at where your robot is supposed to be, and then in terms of your if you're following a target and using trajectory following, you can just see where it's supposed to be and then see if it's actually there and the error and how much PID you're kind of like accounting for, or how much error you're accounting for. So that's the end of my presentation. If anyone has any questions on any of this or just tips you want to know about, you can start asking any questions.
That is super cool. And the sim is that's a really cool visualization of filtering. So for yes, this will be posted. I'll post it everywhere. I posted a link to this, and it'll be on Chief Delphi as well. For the standard deviations, how do you tune those, and do you adjust those with distance or based off of anything live, or do you just keep a static value?
Yeah, so for the start, when you want to tune these values, a lot of times it's just a lot of guess and check work. So you drive around the robot, see how much error you had, see how much like difference you had within your camera like estimates. So if a lot of your camera detections are really far away, even though you're really close to the grid, that just means your camera detections are really noisy. So you want to increase your standard deviations. And then you kind of just play around with this over time. A lot of this tuning can be done in log replay if you're using Advantage Kit. So you can just record all your data on the field once, and then you go in and you can just change your standard deviations and then see how that actually plays out within sim, and do this over and over again. So we were able to do this within one night with log replay. So when you're talking about like scaling your like standard deviations based on distance, that's something that we do. So we do the square of the distance from the actual April tag. So if we have something like 0.25 for our standard deviation, that might become like 1 or 1.25 if we're like 5 meters or 10 meters away from our actual April tags. But if we're really close, that value might just be 0.25. So scaling is really important when you go farther away because you'll have more noise within your April tag detection. And the actual scaling that you do doesn't have to be like a square. It can just be like, you can just do like logistic regression and just do a bunch of like different points that you come up with over time. And then you can just like scale it up and then figure out other points just using logistic regression. Any other questions? Yeah, so okay. Kalman filters is kind of a more confusing topic. So from what I understand, it uses state space control in order to take in a bunch of different points or different like readings and then like composite it together into just like one overall like detection. So a particle filter is kind of a Kalman filter, except it works in a nonlinear space compared to like a linear space. So if you want more like info on that, the WPI Labs like documentation has a really good explanation of it, but I don't really have like a good way to explain off the top of my head.
Yeah, it's complicated. I think it's a mathematically good way of combining different estimates of the same thing.
Yeah.
So you have your odometry from your wheels, which is a very precise estimate in the short run, but over time, you're adding up, you're integrating, so you're adding up error over time. So that is going to be, your odometer is going to be very effective in the short term, but over the course of a match, will get off. Whereas April tags are kind of the opposite. In the short term, they might be bouncing all over the place, but their error is going to be, it's going to average around 0 over the course of a match, right? So it'll be reliable no matter when it is. So a Kalman filter is a mathematically optimal way of combining those two things or other measurements you choose to have, and knowing sort of what data to trust over what timeframes.